Okay, so today I will be talking about nuclear shielding, deshielding, and more. So on the agenda, I'll be talking about the history of NMR, just a brief history. I'll be talking about resonance, NMR, R stands for resonance, so we'll be talking about that. I'll be talking about electronegativity, chemical equivalence, nuclear shielding, and deshielding, and those are just three factors that kind of impact our NMR spectroscopy, our analysis. And I'll be talking about chemical shift, which is a component of our NMR graph. So jumping right in, talk about the history. So the main name when we talk about NMR, he came up with the basis, is Isidor Isaac Rabi, and he was born in Austria in 1889. And then in 1890, he and his family moved to the United States, where he completed his education and his career. He got a PhD from Cornell for studying the magnetic properties of crystals. He also worked with Bohr, Pauli, Stern, and Heisenberg during his career. And I talked about Bohr, Pauli, and Stern in my previous presentation. And Rabi actually used Stern's beam concept from the Stern-Gerlach experiment. And he took that idea and he tinkered with it, and he was able to make an apparatus that allowed him to measure single spin states of nuclei, which is the basis for NMR. And he didn't come up with the NMR machine, he came up with this concept, and then more scientists and engineers jumped into this concept, and then eventually the NMR machine was created. And Rabi won the Nobel Prize in 1944 for his discovery. And one other interesting thing about him is he was very peace-oriented. He wanted there to be peaceful uses of nuclear energy, and he actually rejected Robert Oppenheimer's proposal for him to join the Manhattan Project. So he was a very morally upright and classy man. So next we'll talk about, well, just kind of a brief recap about my last presentation. I talked about how nuclei have spin and magnetic moment. And then if we apply an external magnetic field to nuclei, we will get two energy states. If we don't have nuclei that are spin active, or we don't have a magnetic field, we won't get this difference in energy. We'll only have one energy state. But if we have a substance with nuclei that are spin active or NMR active, they have magnetic moment vectors, and we have a magnetic field, we get this energy difference. We get an alpha state in which the magnetic moment vector of the nuclei is aligned with the field. And then we have the beta state in which the magnetic moment vector is aligned against the field. And so there's this energy difference between these two states. And as the strength of the magnetic field increases, this energy difference will also increase. And so this is where we start. This is the basis. So what can we actually do with this? So we can induce something called resonance, nuclear magnetic resonance. So if we apply a frequency, an NMR, it's a pulse of a range of frequencies, we can supply energy to the alpha state. And when given the alpha state absorbs enough energy, it can actually flip, the magnetic moment vector can flip and align against the field, and it will jump up to this higher energy state, the beta state. And this will happen momentarily, and then it will fall back down, and it will realign with the magnetic field, and then it will emit a signal. And that is the NMR signal that we collect, and that is where we get our NMR graph. So that's just a basic general overview, and this is not really specific to any one type of NMR, proton NMR or carbon-13 NMR. This is just a basic, like any nuclei that is NMR active, this is the basic general concept. So the next thing we'll talk about is nuclear shielding and deshielding, and this has an impact on our results on our NMR graph. And so we talked about neutrons and protons in my last presentation, but this time we'll talk about electrons. So electrons do play a role. They're moving charges. So we're going to talk about two different situations. So here on the left, I have a hydrogen plus ion, or it's just a proton. And then over here, I have a hydrogen atom with one electron, and it is going clockwise around the nucleus. And so let's imagine we apply a magnetic field, B0, to both of these. And on the left here, this proton is going to experience the full effect of B0. There's nothing stopping it from experiencing. That's a pretty normal situation. But then over here, we have this electron, and it's moving. It's a moving charge. Therefore, it's going to generate a magnetic field. And so if we can use the right-hand rule, we can put our thumb in the direction of the charge, and then we can crawl our fingers around, and then we see that the electron's magnetic field is pointed downward. And so as you can see, the electron's magnetic field, will counteract some of B naught, and so this hydrogen atom will not experience the full effect of B naught. Some of it will be counteracted by the magnetic field generated by the electron. And so there will either be a full effect of the magnetic field or a partial effect of the magnetic field. And graphically this is called what we call deshielded. There's nothing stopping the nucleus from experiencing the full effect of B naught. And this is called shielded. There's this electron and it's stopping the nucleus from experiencing the full effect of B naught. Graphically, what happens is, let's imagine that this is our deshielded situation. We've got a standard energy difference here. And so if we add in that electron, if we add in that shielding, we're not going to get as strong of a net magnetic field. The net effect of that won't be as strong. So that's just the same as decreasing the strength of the magnetic field. So what's going to happen is our graph will kind of scrunch together and look like this. We'll have a lower energy difference. And so what this does is, if we have a different energy difference between these two situations are going to require two different frequencies to induce resonance. And so our alpha state will require a different amount of energy or a different frequency to get it to jump to the beta state. And so we have different frequencies, and that's part of why we get some different peaks in some different electronic environments. And this is most likely better illustrated if we actually look at some molecules. So on the left here I have methane, and on the right here I have ethanol. And let's imagine we're going to do proton NMR on both of these. In the case of methane, we have 4 hydrogen atoms and bonded to carbon in a tetrahedral structure, and it's a single bond in every situation, and they're equally spaced. So all of these have identical electron environments, and so they'll all require the same frequency for resonance. And so in this case, we'll get 1 peak on our NMR graph if we did proton NMR. In the case of ethanol, it gets a little more complicated. We're actually going to get more than 1 peak because we've got this hydrogen here bonded to this oxygen. We've got this hydrogen on the right side bonded to this carbon, and we've got these 4 down here, 2 on the left and 2 on the right. And so we'll actually get 4 peaks because we've got 4 different environments, 4 different frequencies that are required for resonance for these nuclei. And so, yeah, we did proton NMR, and then chemical equivalence, we can describe these hydrogen and methane as chemically equivalent to one another because they have identical electronic environments, and they will generate 1 peak on our NMR graph. Whereas over here, the only nuclei that are going to be chemically equivalent are this pair down here will be chemically equivalent, and then this pair over here will be chemically equivalent to each other. And so moving on, the next thing we'll talk about is electronegativity. And we learn about electronegativity even in high school chemistry, and its basic definition is how badly an element wants an electron. We learn about how the right side of the periodic table, these elements really want that last electron to get octet stability, whereas on the left side they have like 1 or 2 electrons in their valence shell, so they're not as concerned, and they'd be more likely to give up their electron. And so a more electronegative atom will have a higher electron density. And if there are more electrons or less electrons, that will have an effect on the shielding that we just talked about. And so if it affects shielding, it'll affect the net effect of the magnetic field that a nuclei feels when we do NMR. And then that will affect where our peaks are on our NMR graph. So, and we can kind of think of an example, like if we had fluorine bonded to hydrogen, or carbon bonded to hydrogen, these would be 2 very different bonds. The fluorine is very electronegative compared to the carbon, and so fluorine would have a higher electron density than carbon, and so that shielding, that electronegativity will affect the shielding between those 2 bonds, and we'll have some different peaks in that situation. So I've also circled some of our NMR active elements here. We've got hydrogen 2, carbon 13, fluorine 19 are common ones. And of course, electronegativity doesn't really affect how effective a nucleus is in NMR. It's just something to consider. Just because something's really electronegative doesn't mean that it's better for NMR. It really depends on if it's actually spin active for NMR, but it's just something to consider. So the connection here is between electronegativity and shielding. The frequency at which nuclei are resonant will change depending on the electronic environment. And so that will affect our location of peaks. Different electron environments, different peaks. And so one thing about the NMR graph, if we go downfield, we'll have higher electronegativity for these electronic situations. And by these graphs, we know that there are different electronic environments, and so we can infer some molecular structure from an NMR graph. This is the carbon 13 NMR for ethanol, and so this peak corresponds to this carbon 13 here in the center, and that's different from this peak, which corresponds to this carbon 13 connected to these 3 hydrogen on this side. So finally, we'll talk about chemical shift, and chemical shift can also be called fine structure. And this is kind of difficult to understand if you're not familiar with NMR, because we get a frequency, we get a signal from doing NMR. So it's kind of confusing, like, why do we have this thing called chemical shift? Like, we get frequency, that makes no sense. Well, chemical shift is what we do. And so when we do NMR, we compare to a standard compound. And a lot of the times this is tetramethylsilane. And it has a chemical shift of 0, which makes it useful when we have some samples and we want to see what the difference is between the tetramethylsilane and any of our given samples. Any good experiment, you need a control. And so chemical shift is actually calculated with this equation. Chemical shift is a lowercase delta, and it's equal to the frequency signal from the sample minus the reference frequency divided by the spectrometer frequency times 10 to the 6th. And so it's multiplied by 10 to the 6th because the spectrometer frequency is on the order of megahertz, or 1 million hertz, and the sample frequency is on the order of hertz. So in order to get a friendly number, we need to multiply by 10 to the 6th. So if I were to put in 215 hertz for this sample, and then I put in 0 for the reference, and then I divide by the spectrometer frequency 100 million hertz, and then multiply by 10 to the 6th, I will get 2.15 for my chemical shift. And I could do that for any of these situations, and I would get the corresponding chemical shift. Chemical shift is also measured in units of parts per million, and this makes sense as we've got hertz and then million hertz on the bottom, parts per million. So that also, everything adds up, it all makes sense. So in summary, talked about the history of NMR, Isidore Isaac Rabi, who came up with the concept of NMR, the concept of nuclear spin. I talked about resonance, NMR, what resonance is. I talked about electronegativity, nuclear shielding and deshielding, and chemical equivalence, and the effect that those have on our NMR graph and our electronic environments. And then I talked about chemical shift, which is an element of our NMR graph. So our presentation schedule, last time I presented on spectroscopy, atoms, and spin. And this time I presented on nuclear shielding, chemical equivalence, electronegativity, and chemical shift. And so these 2 presentations were combined together in order to make more time for the final presentation, NMR applied to polymer-derived ceramics. So thank you. Any questions?
Thank you very much.